Right, welcome back. So, time to look at some graphs. I've done my intro. I wasn't going to show you the fast mission setup because I've already done a video on that. But what the heck, let's just show you it again. It was very fun. So here we go. Fast auto mission. On a nice sunny day. Could do with one of those. It's not sunny at the moment. Oh, it's dark at the moment because it's night time. But, so fast mission in a box pattern and RTL.
Still pretty close to the takeoff.
And a bit of a landing. Alright, so enough of that. Alright, so that was my beta, which I've got here. You can see there. And I'm going to look at some graphs, particularly to look at the M10, Holybro M10 Micro. So if you remember, I've got this setup here. So I've got two GPSs side by side, and that makes it easy to compare the performance of the GPSs. And if you remember, one of those is a Matek M10Q, which is sort of my go-to part for a lot of my drones, and then the other is, in this case for this video, is the Holybro M10 Micro. So very similar. Those are the vendor's items I'm using, but a lot of this is about the chipset and the antenna that's used. I know the Matek uses a U-Blox antenna, so it's quite high quality. I suspect the Holybro might be similar, slightly different chipset, but obviously a much larger antenna, which can help. So let's look at one of the first logs I did. So if I pull up the map here, so you can see I'm flying in this box pattern around a field, and you can see we've got GPS is the blue estimate, GPS 2 is the green estimate, and then red is the position estimate. So a couple of interesting things here is one is you can see that the position estimate goes way out at the top here, and also you can see that the GPS estimate is quite badly wrong for GPS 2 here. Now in this setup, GPS 1 is the M10 Micro and GPS 2 is the M10Q, so the smaller one. So we would expect GPS 2 to be worse. The question is by how much and what are we going to do about it? So a couple of things to look at from this graph, the sort of things that I was looking for, and this you'll see this sort of theme emerge as a look at some of the other GPSs. So first up, I think I'll put the map away just so you can see a little bit better. So first up, look at the acceleration. So given that this copter is traveling almost in a vertical orientation, the Z acceleration probably is the most accurate, and you can see here we're hitting 5Gs at points, usually in the corners, so that's good. That means I'm getting above my 4G limit, which I talked about last time, the sort of kinematic model, 3D 4G. So that's good. And then what we can look at, I showed this in the other video just about the fast missions, is looking at the innovations for that the EKF has for these two for these two flights. So we've got velocity innovations getting pretty high. So anything above 1 is bad, and so we get way high on here. Velocity innovations on the first GPS is really bad. velocity innovations on the second GPS much better. So we sort of survive. We don't get above 1. So GPS 2 much better from a velocity innovation perspective. Similarly, if we look at position innovations, see position innovations are better. So the velocity innovations are quite bad. Position innovations for GPS 1 get to 0.5, which seems good, and second GPS is lower, but still good. So that looks okay. All right, so let's look at the height innovation. Okay, so height innovation is horrendous, and it's horrendous on both. And the reason for this is because we're using the barometer for the Z estimate, for the height estimate, and you can see that that's just horrendous. The innovations get up to above 3, so that's not good. And then mag innovations are not too bad, which, you know, it's using the same. In these tests I used the compass on the second GPS on the Matek, just made it a little bit easier to set up. It's positioned reasonably far away from the battery, and so there's a bit of interference, but, you know, very high currents. I'm cruising around at very high speeds. I think probably we can have a look at the current. If we have a look here at the battery, what current do we get up to here? So here's the current. So okay, so we hit 90 amps, which is a decent amount of current, and is going to produce a decent amount of interference. And you can actually see the interference is relative to the current. So although I've got compass motor compensation switched on and calibrated, it's still struggling with this level of current. So so mag's okay, but height is horrendous, and I think so. I think that's the two things to notice from the logs are I'm not getting much above my 4Gs, and that height is horrendous. Now the height is horrendous because of this. Because we're using the barrow for height, and so the obvious thing then to do is try and use the GPS for height instead. So if I look at so this is in the EKF, and this is all in the XKF4 messages. So there's a square root of the variances of different kinds, so we'll get rid of those. But the other interesting message to look at is GPA. So this gives you some additional information about the GPSs, in particular their accuracy estimate. So if we look at the height accuracy estimate for 1, this is in meters, so GPS 1 and then GPS 2. So you can see that GPS 2, the height accuracy is much worse than GPS 1, and GPS 1 is within 2 meters, which is, you know, it's a decent distance, but it's not, that's not horrendous. Like, you know, if I'm within 2 meters, as long as I'm high enough, I'm not going to crash. So actually using the GPS for height is probably not an unreasonable thing to do. And given if we have a look at, if we compare the altitude of the barrow with the GPS, which we should be able to do in this, not ATT, sorry, here, the CTON message. So if we look at the barrow altitude, you can see that's all over the shop. And then if we look at oh, I've got to do this weird. This comes from the GPS message, so we can see alt here, but the GPS altitude is absolute, and the barrow altitude is relative. So you can see that the Barrow, and if we sort of take this 0 as the reference point, I mean, Mission Planner has done a reasonable job, but you can see there's quite a large diversion between the actual height, because we think the GPS is within 2 meters, and what the Barrow is saying. So the Barrow is pretty inaccurate here, and so I think using the GPS for height makes quite a lot of sense. So let's bring up the next graph. So I think, sorry, the other thing, just before I do that, the other thing to show you was just going back to the map. So you can see here that the angles, the cornering is extremely sharp. And this is because I've got my waypoint radius set quite small, so it sort of tries to get quite close to the waypoint radius before it makes the next turn. And this means I can't do very fast turns. It means it has to decelerate into the turn in order to hit the waypoint radius before going around. So this is relying on S-curves. So in order to get faster cornering, what I want to do is increase the waypoint radius, and then I should get much smoother turns, which allows me to do them much faster and not have this constant acceleration and deceleration. So that was sort of the learning from the first log that I looked at. So let's take a look at the next one. So I'll pop that one away, pop this one up. Okay, so this log is using GPS for the height estimate. And so first thing we want to do is look at XKF4 and see what the height innovations look like. And you can see that they are, in fact, much better for, so we can see events. You can see that they're actually much better for, in the main, for the second GPS. So this is this green line here, and that's actually the Matek M10Q. So both are better, but the height innovations, the second GPS is better than the first GPS, which is kind of interesting. Now, one of the reasons that might be is that one of the changes I made in this flight, so well, a couple of changes I made. So height innovation is better because we're using the GPS as our source for height, for altitude. Look at the map. Okay, no, I didn't change this one, so this is still cornering with fairly sharp corners. But one of the changes I did make was to set the update rate for the GPS higher. So by default, the update rate is 5 Hertz, but you can ask the GPS to send you data at 10 Hertz. Now, the problem with that is that some of the time the GPS can't cope. So if we look at, and the key message here is GPA again. So if we look in GPA and look at delta, this is basically the time between data updates on the GPS. And if we look at, so number one is the Matek, and delta, you can see, oh, we're getting some dribs and drabs there. Oh. And the M10 is worse. It was interesting. My recollection was these were the other way around. Anyway, you can see that. Oh, and sorry, no, you can see that I've only done it for one. So this is in milliseconds essentially. So 100 milliseconds is 10 Hertz. 100 milliseconds between updates. 200 milliseconds is 20 hertz. Sorry, 5 hertz. So the first GPS is running at 10 hertz, sorry, at 5 hertz and doing okay. The second GPS is running at 10 hertz, and we're getting these delta dropouts. And any sort of timing jitter here means that the EKF gets very confused. So this is a very, very bad thing, and basically shows that you can't run this this GPS, which I think is the Matek. I want to say it's the Matek. Can't run this GPS at 10 hertz. You've got to run it at 5 hertz. All right. So one more from this series. Right, so let's have a look at the map. This one. And similarly, trying to go a bit faster in this one. So if we look at the IMU, you can see that the acceleration is still getting down to 5 hertz, but this is because of the cornering that's the problem. And if we look at the height innovation, it's better, still better on the first GPS than it is on the second GPS, which is interesting. The other thing I should say here is that to do this testing, what I've got set up is EKF affinity. So the EKF is using a separate, each EKF is using a separate GPS and a separate IMU. And so this is to enable me to compare quite closely. So okay, so those are sort of my initial setup graphs. So basically 10 hertz is a no-go, 5 hertz is better, use the GPS height rather than the barrow height. And then I started to do some proper testing. So let me show you the first graph of that. Alright, so this was my day 2. And if we look at the map again, you can see this time, because I've reduced the, increased the waypoint radius, I'm getting these much smoother curves. We've still got some divergence between the GPSs, but things are a bit smoother. And if we look at the acceleration, I'll get rid of the map, look at the acceleration for the IMU, which is here. Okay, acceleration Z, you can see we're getting to 7.5 G at point, so much higher acceleration, which is great for this test. And we're going, I think I was set it up to 40 meters a second go, so going pretty quick. If we look at the height innovation, first of all, we'll just have a quick look at GPA and the deltas. So you can see deltas were running at 5 hertz, and that looks good. So basically just 10 hertz just doesn't work on these M10s, it can't keep up. So deltas 5 hertz is good. And if we look at the vertical accuracy, you'll see the first one 2 meter accuracy, second one is 3 meter accuracy. It makes me think that perhaps I've got these the wrong way around. I wonder which is which. It's kind of difficult to tell though. So if the messages tell us anything. Right. U blocks to well, they're both M10, so we can't tell. They both show as SPG 5.10, so there's absolutely no way to tell them apart. Same firmware version. Yeah, I have to guess. I think still that number 2 is the M10 Micro, but I could be wrong about that. So if we look at the height innovation, so we can see here that the height innovation is now much better, even though we're going faster with high acceleration. Oh, interesting. Okay, so height innovation is better and much better on the first GPS, which is kind of what I would expect. So the height estimate clearly, as far as the EKF is concerned, is much better on this on the M10 Micro. Whereas on the M10Q, it's getting up above 1, which is bad, not great. So height innovations for the M10Q not good, but for the M10 Micro actually pretty good, and it doesn't get above a half, so that's actually pretty good. So we look at the position innovations. You see the position innovations are getting quite high on the M10, up to 0.7 to Micro. And then if we look at the M10Q, it's similar. So similar position innovations, which may be something to do with the vibration. And then velocity innovations on the first one, still not great velocity, just creeping above 1 there. And on the second GPS, quite a lot higher, getting up to 1.6. So I think this is probably what we would expect. The velocity innovations quite high, given the accelerations that we're hitting, but better on the M10Q than on the M10 Micro than on the M10Q, which is a regular M10. And then mag field, similar. Got reaching half here, and I suppose just for completeness I could compare what current we got on this run. So current is here, and again you can see we get up to 90 amps, so very similar, very similar. And then back to the GPAs, if we compare height accuracy, interestingly, so the M10Q, which is this green line, was aware that its height was much worse than the M10 here. So it definitely was aware that that wasn't so good. Velocity accuracy, again, second GPS not as good. This green line here, sort of getting on for double. And then the speed accuracy. So on the first one, reaching sort of 1.35 meters a second, and on the second one, reaching 5 meters a second. So this will result in quite a large position error where if the speed accuracy is very wrong, because sort of the integration of the speed won't work very well. So all things pointing towards the M10, which is the M10 Micro, working pretty well, the M10Q working less well, but overall a pretty pleasing result. And even with those estimates, you can see that it'd be nice to know where the actual desired track is here because of the S curves, because you can see the square box here, but it'd be nice to know what we think this should be tracking for both of these. Not sure how you show that. All right, so that's quite enough of me talking for now. 25 minutes on the M10 Micro, but looking pretty promising, and I'm sort of pleased with those results. So next video I'll look at the M9M, comparing that in a similar way, and then the F9P. So we'll see how that goes. Thanks for watching.